In this video, we're going to take a look at three operations that can be performed on categorical propositions that result in a new proposition. So these will be the operations of conversion, obversion, and contraposition. And depending on which operation that we are performing, and depending on which categorical proposition we are performing that operation on, the new proposition, the new statement, will either be logically equivalent to that proposition or it won't be. So that's why we're investigating this. We want to be able to identify when such an operation has been used or is instantiated between two propositions, and then we want to be able to identify whether they're logically equivalent or whether they're not. And the reason why we want to know whether they're logically equivalent is because if you have an argument where one of the premises is a proposition that you would start with, and then the conclusion is a logically equivalent proposition, then you know you have a valid argument. Right? So this is a way for us to be able to identify valid arguments, especially when they're just an immediate inference, when you have only one premise that goes directly to the conclusion. So we're going to start by looking at conversion, the operation of conversion. On the left side of these two columns that we have, these represent the propositions that we start with. So our A propositions, our E propositions, our I propositions, and our O propositions. The column underneath conversion represents the new proposition that we get as a result of applying the operation of conversion to these original standard form categorical propositions. So what takes place in conversion is just a switching of the subject term and the predicate term. Doesn't matter if it's the A, E, I, or O, that's all we're doing. So notice if we take a look at this A proposition, since it says all A are B, if we flip the subject term and the predicate term, the new sentence that we get is all B are A. So this is a converted proposition of our original A proposition, all A are B. So likewise, just the same pattern. If we look at this E proposition, then by switching out the subject term and the predicate term, instead of no A are B, we get no B are A. So likewise, from some A are B, when we convert, we get some B are A, because those just switch the subject term and the predicate term from each other. And then some A are not B. When we apply conversion, we get some B are not A. Pretty straightforward, I think. Obversion and contraposition, we'll see, are a tad bit more involved or difficult. In order to successfully perform obversion on a categorical proposition, we need to perform two steps. We need to change the proposition's quality. So if the proposition, the original proposition, is affirmative, the new proposition needs to be negative. Likewise, if the original proposition is negative, then the new proposition needs to be positive. But we also need to replace the predicate term with its term complement. So if our predicate term is P, where P is a variable for any term, so if our original proposition, the predicate term is P, then the new predicate term in the new sentence needs to be non-P. Likewise, if in the original statement that we perform obversion on is non-P, then in the new proposition that we get after performing obversion, it needs to be P. So again, in our left column here, we have our A, E, I, and O statements in standard form. And then the right column tells us the result of performing obversion on these standard form categorical propositions. So if we start with our A proposition, first we note that it's an affirmative proposition. So we need to make sure that the proposition we end up with is negative. Of course, we're not told to change the quantity, so it needs to remain universal. And that's going to give us no, because that's the negative universal. And then since B is our predicate term, then we need to make sure that we get its term complement, which is non-B. So we end up with no A or non-B as the result of performing obversion on an A statement, all A or B. So then for our E statement, again, we have a universal proposition, but this time it's negative. So we need to make sure to keep it a universal proposition, since that's not one of the things that we're changing. But we do need to make sure that we have the affirmative version of a universal statement, which is all, as opposed to no. Again, our predicate term is B, so the term complement of B is non-B. So all A or non-B is the result of performing obversion on no A or B. For our I statement, it's particular and affirmative. So we need to make sure that we're going to have a particular negative statement. So for our particular statements, the negativity or positivity, the affirmative or the negative aspect, is located or communicated to us in its copula. So since we have the affirmative R in some A or B, we need to make sure that we change that R to R not. And since we have B, the term complement will be non-B. So from some A or B, we get some A or not non-B. So our O statement is the negative particular statement. So again, we locate the negativity in its copula, and we need to go from it being negative to affirmative. Again, B is our predicate term, so its complement is non-B. So obversion performed on our O statement, some A or not B, is some A or non-B. With contraposition, we again have two steps. One of our steps is we switch the subject and predicate terms. So basically the first step is conversion. So we would switch out the A and put it in the predicate place, and we put the B in the subject place. But then we need to additionally replace both terms with their term complements. So being that we have A and B here, and the term complement for A is non-A, and the term complement for B is non-B, then we will end up with non-B in the subject placement, and we'll end up with non-A in the predicate placement. Of course, if it was all non-A or non-B, then we would end up with B in the subject placement. We'd end up with A in the subject placement. All right, so again, 2 steps. One is basically conversion, and then on top of conversion, we replace both terms with their term complements. So if we start off with all A are B, as in an A statement, then by switching out the terms and then replacing them with the term complements, we end up with all non-B are non-A. So then if we have no A or B, by switching out the terms with one another and then replacing them with their term complements, we end up with no non-B or non-A. If we have that some A or B, then by replacing the terms with one another and replacing them with their term complements, we end up with some non-B or non-A. And again, if we look at this O statement, some A are not B, we switch out the subject and predicate terms for one another and then replace them with their term complements, and we end up with some non-B are not non-A. So now let's look at a chart that tells us when the operation ends up with what would be a legitimate inference. So to the left of this line, we have our A, E, I, and O propositions. And then in our conversion column, if we apply conversion to an A proposition, and then we maintain that the resulting proposition follows from the original A proposition, that would be illicit, which means the inference would be a bad inference. It would be invalid, an invalid argument. But if it's an E proposition, it would be legitimate. So for example, we have no A or B, we perform conversion on that, which gives us no B or A. Those are logically equivalent propositions. And so if the proposition on the left, no A or B, is a premise, and no B or A is a conclusion, then we would have a valid argument. So the same would be of I propositions. Some A or B is logically equivalent to some B or A. So that would give us a legitimate inference. But it'd be illegitimate for our O proposition. Some A or not B is not logically equivalent to some B or not A. So then if we look in the Obversion category, we'll notice that Obversion always gives us a logically equivalent sentence. And so any argument in which an A proposition, E proposition, I proposition, O proposition is a premise, and then the relationship between it and its conclusion is such of Obversion, then we would have a valid argument. Then if we look at contraposition, if we have all A are B, and we perform contraposition on it so that we end up with all non-B are non-A, those are going to be logically equivalent. And since they're logically equivalent, if one is a premise and the other one's a conclusion, that'll be a valid argument. But for our E and I propositions, that would be illicit. It would give us invalid arguments because those propositions are not logically equivalent. But they would be logically equivalent if it's an O proposition. So this chart can help you determine very quickly with immediate inferences, if they're categorical propositions, whether we have a valid argument or an invalid argument on our hands. And we can even use Venn diagrams to prove this to ourselves. So take premise 1 here, all A are B. We were just discussing this example. The conclusion is the contraposition of all A are B. So all non-B are not A. I maintained on the previous chart, on the previous table, that is a legitimate inference. So we would have a valid argument. So look, if we, in this top Venn diagram, if we diagram the first premise, we will see that in order to make all A are B, to represent that on our Venn diagram, we have to get rid of the second area, what I'm going to label as the second area. So I shade this area out. Now we're left with all A being within the B category, so all A are B. And then if we look at all non-B are non-A, so again we have our 4 areas. And now I need to find my non-B's and my non-A's. So here's a non-B. There's a non-B. And we have non-B's in area 1. And we have non-A's in area 4. And we have non-A's in area 1. And what we're told is that everything that is a non-B is a non-A. But in 2, if we do not shade that area, we have non-B's that are A's. But we're told that all non-B's are non-A's. So in order to make it such that everything that's a non-B is a non-A, we have to get rid of area 2. Leaving, of course, all of our A's to be B's. And so the shading is exactly the same from our first premise and our conclusion. And that tells us that those are logically equivalent and that the argument that we have up here is in fact a valid argument. So now let's look at a case that's illicit. Looking at this argument, we have some A are not B, and the conclusion is that some B are not A. So what we have here is a case of conversion, because from premise 1 to the conclusion, all we have done is switched out our subject term to the predicate term and our predicate term to the subject term. So if I look at premise 1 and I want to represent what that commits us to visually on a Venn diagram, it tells us that some A, there exists an A, and that A that exists is not a B. So given part 1, part 2, part 3, and part 4, or area 1, area 2, area 3, and area 4, if I want to show that there exists an A but it's not a B, I need to make sure that I put an X in the A circle, but that's outside of the B circle. Then for the conclusion, we're told that some B are not A. So I need to make sure to put an X in the B circle that's not inside of the A circle, which is area 4. So notice then that the information that's contained in the conclusion, it contains more information that's contained in the premise. And so we can't move from the information that's contained in the premise to the conclusion, to the information that's contained in the conclusion. You can't do so validly at any rate. So in this case, we have an invalid argument, which is why it's an illicit use of conversion. So here's a helpful way of remembering when the use of conversion and when the use of contraposition gets you a legitimate inference. So if we look at the second and third vowels of each of these words, we have, in the case of conversion, E and I. So if we start with an E proposition or an I proposition and then we convert it, the new propositions that we get will be logically equivalent to our original propositions. And so you would have a legitimate inference from one to the other. Contraposition, we see that the second vowel is A and the third vowel is O. And indeed, if you apply contraposition to an A and O statement, the new statement that you get is logically equivalent with it. And so moving from one to the other will be a legitimate inference. Then in case of obversion, all you have to remember is that you always get legitimate inferences or logically equivalent statements as long as you perform the obversion correctly. So now we're going to practice applying these concepts. And what we're looking at is the propositions that are across from one another. And first we want to determine whether they're related, such as being conversions, obversions, contrapositions, or contradictories of one another. We also want to know, given the initial truth value of the statements of the left, whether the statements on the right are true, false, or undetermined. So go ahead and look at the first two statements and ask yourself how they're related. If you said they are obversions of one another or obverts, you're correct. And the reason why is we start with an affirmative proposition and we end up with a negative proposition. Not only that, but if we focus on the predicate terms, we'll see that they are the class complements of one another. Well, those are the two steps of obversion, so they're obverts. Now ask yourself, what is the truth value do we know whether it's true, false, or undetermined of the proposition on the right, given that the proposition on the left is false? Since Obversion always gives us logically equivalent statements, and logical equivalency means that they are true in all the same cases and false in all the same cases, being that the statement on the left is false, it's got to be that the statement on the right is also false. So now let's look at the next pair of propositions. Some non-B are A, some A are non-B. Ask yourself how those are related. The correct answer is conversion, because all we have done with the statement that's on the right is to switch out the subject term with the predicate term and the predicate term with the subject term. So we get some A are non-B. So now we need to ask ourselves, given that the proposition on the left is true, do we know whether the proposition on the right is true, false, or undetermined? If you said that they are logically equivalent and therefore we know that some A or non-B is true, given that some non-B or A is true, that's correct. And we can figure that out on the basis of the mnemonic that I gave you in the previous slide. This is an I statement. And since it's an I statement and we use conversion on it, then I know that we're going to get a logically equivalent sentence, statement. And so since some non-B or A is true, we know that some A or non-B is true. Now let's take a look at the last pair of statements. It says that all non-B are non-A. And then we're told that some non-B are not non-A. If you said that these statements are contradictories of one another, you're correct. One thing to note is that we move from a universal statement to a particular statement. But neither conversion, obversion, or contraposition tells you to move from the universal to the particular. So that already rules those out as possibilities. Then if we remember the square of opposition, the Boolean square of opposition, we know that A and O propositions are contradictories of one another. Just as E and I propositions are contradictories of one another. Well, this is an A proposition. All non-B or non-A is an A proposition. And some non-B are not non-A is an example of an O proposition. Since we know that this is false, and these are contradictories, and contradictories must have the opposite truth values, we know that the sentence on the right is true. So we're going to continue practicing applying our concepts. Now for the remaining of the arguments that we're going to look at, we want to determine whether the propositions are related as in terms of conversion, obversion, contraposition, contradictories, or maybe they're not related to each other in any of those types of relationships. And then we want to ask ourselves whether the argument is valid from the Boolean standpoint. So if we look at the first argument, all non-B are C, no non-B are C, ask yourself how these are related or if they're related at all. So one important feature of this argument is that in the premise we have an affirmative statement, all non-B are C, and in the conclusion we have a negative statement, no non-B are C. Well, that rules out conversion and contraposition because they don't ask us to change the quality of our statements. The other thing to note is that our predicate terms are the same. They're not related by complementary class. So that rules out obversion. And the contradictory relationships of A propositions are O propositions, but our conclusion is an E proposition, so that rules out contradictories. So the correct answer here is they're not related at all in these terms of these four relationships. And so from the Boolean standpoint, the argument is invalid. Just because the premise is true, it doesn't mean that the conclusion has to be true as well. So now let's look at the next argument. Some non-B are A. Therefore, it is false that no B are A. Importantly, we have this it is false that in front of this. And it is false that is in front of an E statement. So use that information and see if you can determine whether these propositions are related in terms of conversion, obversion, contraposition, or contradictories, or at all. On our square of opposition, E statements are contradictory with I statements. And of course, when we have a premise, we're implicitly saying to accept whatever we state in the premise as being true. So that means we're treating our I statement as being true, which means it would have to be the case that our E statement is false, because for I and E to be contradictories is for them to have the opposite truth values. So if we start with the premise that some non-B are A, that it's true that some non-B are A, then it has to be false that no non-B are A. So this is a valid argument. So, couple of the features that are important in looking at statements and judging whether they're contradictories or not is whether their subject term and their predicate terms are uniform. And what I mean by uniform is that they are in the subject placement, the same subject placement, the same predicate placement, and they're the exact same terms. So here we have non-B and non-B, both in the subject term, as opposed to, say, non-B and then B in the subject term. or having non-B being the subject term in the premise, and then non-B being in the predicate term for the conclusion, and same sort of thought process with the predicate terms. So now if we look at some non-B are A, therefore some non-A are B, ask yourselves, how is that related? Well, what we note here is that our predicate terms and subject terms have been switched, and not only have they been switched, but they've been changed in terms of their complementary classes. And those are the two steps of contraposition. So here, our propositions are related by way of contraposition. Then asking whether this is a legitimate use of contraposition. We look at our second and third vowels, A and O. So we needed to start with our premise. It needed to be either an A proposition or O proposition, but it's an I proposition. So this is invalid from the Boolean standpoint. Now we look at premise 1 and the conclusion of the next argument. It says it is false that some A are non-B, and it is false that some A are not B. We'll bracket this off for the moment. Notice that we have an I proposition up here and an O proposition here. As so long as we're bracketing off, it is false that. And the some A are non-B is a positive statement. It's an affirmative statement. But the conclusion, some A are not B, is a negative statement. So we have a change from an affirmative statement to a negative statement, so a change of quality. And then not only that, but we, in our predicate placement, we have our complementary classes of one another. Well, those are the two steps of Obversion. So our premise 1 implicitly, by what it states, asserts that it is true, that it is false, that some A are non-B. Therefore, it is true that it is false that some A are not B. Well, since these are obversions of one another, or obverts, they're going to have the same, they're logically equivalent and are going to have the same truth value. Well, they do. We're asserting that they're both false. So this is a valid argument. So it's obversion and it's valid. In our last argument, it says no non-A are non-B. Therefore, some non-A are not non-B. Think about that for a moment and decide how you think they're related and whether it's a valid argument. The two features that should jump out at you first is the quantifiers. So we have no and some, and that's a change in quantity. But conversion, obversion, and contraposition don't have you change the quantity, ever. None of them do. So we're not going to have that type of relationship. But also, the propositions that we have is an E proposition and an I proposition. So there's no way for these to be contradictories. So on the Boolean standpoint, these don't relate to one another in an interesting way, and since they don't relate to each other in an interesting way, we know that is going to be an invalid argument.